Hello, everybody, and welcome to Technically Speaking, episode number 5. It's hard to believe we're already on the 5th episode of 12 this year. Today, we're going to get really deep into the world of vapor pressure, something I like to call Psychrometrics 301. It's going to be a fun episode. It's going to be very, very technical today, probably the most technical episode that we've had so far. But as we typically do, we'll start off with some of the technical information and we'll wrap up by simplifying things and putting it into practical terms. So let's go ahead and buckle up and get ready for episode 5. Again, for those that are just joining us for the first time, my name is Brandon Burton, and I'll be your host today. I'm the Vice President of Technical Application here at CoreLogic and NextGear Solutions. I'm also the Chairman of the ANSI ICRC Standards. One of the things that I really love about running these webinars is the ability that I have to connect to you in industry and ensure that you really have a direct access into the ICRC and ANSI standards. So outside of running these webinars, which I love to do, I spend a lot of my time managing the development of our industry standards. So keep that in mind. And as I share my contact information with you a bit later, don't hesitate to reach out to me for anything that relates to the cleaning, restoration, and inspection industry and our standards. Here to support everything we do in our industry through standards. So keep that on file. With that, let's go ahead and get started into today's episode with a little bit of housekeeping. Keep in mind that as we go through these webinars, we don't keep the chat open during the webinars, but what we do use is the Q&A tool. So if you're not real familiar with Zoom, you may want to find that now up in your top ribbon, and depending on your platform, it may be at the bottom, but typically at the top, you should be able to open up the Q&A tool. And as we go through the session today, at any point, drop any questions you have into that Q&A tool. At the end of the program today, I'll go through all of those questions and we'll have a live Q&A period for those of you that are attending this live. Those that watch the recording afterwards, the Q&A session is not included in that. We don't record the Q&A, but for those of you live, ask me anything and I'll do my best to answer it. So with that, let's jump into today's episode. So today we're going to talk real deeply about vapor pressure. And there's a very, very specific reason why the vapor pressure is something we're going to spend so much time on. It's one of the primary forces behind your drying rates in water damage mitigation. And all of the things being equal, the greater the vapor pressure differential, which is a phrase you'll hear me say a lot today, the faster your drying rate is going to be. And because drying rates are so important for preventing damages, for reducing the amount of time necessary to dry, it's a really important tool to understand. It's not something you're going to use every single time that you're trying to dry a building material, but you're going to use vapor pressure a lot when you're dealing with challenging assemblies, when you're getting a significant amount of pressure for the drying rate specifically, especially in special circumstances. And when you're dealing with really highly sensitive materials, finishes, and contents, and it's critical to ensure that we're in absolute control of what's happening in the environment. Your typical, drying process, because of the amount of time it can take to really sit down and evaluate vapor pressure, I would not advocate that you do it on every material and every job every time. It just isn't practical. But I would say in many projects, it's at least a few areas where you're going to need it. And in some projects, there are a lot of places where you're going to need it. So it's important to understand and understand the driving forces behind it, the math behind it. We're going to get into it pretty deeply from a number of different angles. So first, to kind of set that up, as I like to do, I like to start by reviewing some of the basic principles that we've already talked about to set up the conversation. So we're going to start with a bit of review, like we typically do. Then from there, we're going to get really deep into the math behind vapor pressure. Not just the psychrometrics, but the math. It's really important to understand the math so you understand the reality of what vapor pressure may or may not do for you. And then from there, like we typically do, we'll round things out into the practical. So that'll be kind of the order of operation today. Let's start off with our basic review of the psychrometric principles we've discussed in previous episodes. So in our review, the first place that I want to start with a couple of models that we discussed. The model primarily defined as H.A.T. H.A.T meaning humidity, airflow, and temperature. It's an important place to start because this helps us kind of ground ourselves in the basics that there are really three psychrometric entities, you could call them, or principles of air that influence the rate of drying. The amount of moisture that is in the air, the humidity, has a direct impact on drying rates. The temperature in the environment, and by environment, I mean both of the air and the material that you are drying, both have a very important impact on the rate of drying. And so does air movement, right? And if we remember some of the basics about each of these three, humidity and temperature are the qualities of air that give me the means to support evaporation, the means to take on additional water vapor from the building material. Air movement is what places those conditions directly in contact with the building material surface where evaporation is occurring, or at least where the water vapor is available for transport. And temperature is interesting because temperature has a couple of different influences. Temperature, not only in air, because temperature is what keeps that moisture suspended. It's the energy that allows that moisture to remain in suspension. If I don't have enough temperature, the moisture settles back out of the air very, very quickly and condenses. And it also directly impacts the way moisture moves in a material. The material temperature, I would argue, is actually more important than the air's temperature as it relates to drying. In fact, some of the fastest drying processes in the world don't use very warm air. In fact, some use very cool air, but use very warm building materials, because that's where the energy is directly impacting evaporation, is in the material where the water actually exists. So we'll kind of dive into that and analyze it a bit deeper as we go. Another way that we looked at H.A.T, or humidity, airflow, and temperature, is by applying H.A.T onto a timeline, just in fact, the most recent past episode. We looked at how humidity and temperature weren't as important early in the drying process, where water is available at the surface, right, where you could physically make your hand damp by touching the building material. What was most important in that phase was air movement, a transportation system to remove that evaporating water from the surface. But as we went deeper into the drying process and got into what we called the falling drying rate and eventually into bound water, air movement really starts to tail off for importance. And what becomes more important is control of humidity or lower humidity and control of temperature. And if you want to be really precise, a warmer building material. And that really sets us up for today's discussion, because vapor pressure or vapor pressure differentials are all about controlling the air's humidity and controlling the material's temperature. Those are the two elements that we're going to have the more precise control over when we start manipulating vapor pressure differential. And this model really shows that. It really shows how important that becomes as we get later into that drying cycle. So with all of that said, we began looking at the psychrometric chart in the last couple of episodes and really defining some of the elements that we can evaluate on a psychrometric chart. The really basic elements on the psychrometric chart are things like the temperature, which is down at the bottom of the psychrometric chart. This really fancy thing called dry bulb temperature, which we have to say because, believe it or not, there's such a thing as wet bulb. Relative humidity, which are these curved lines that move through the middle of the chart. And humidity ratio, which is the most common thing we're calculating with a chart, right? And that's on the far right-hand side. We added to that in the most recent episode what I called the more advanced psychrometrics, a better look at heat and energy and things like enthalpy, vapor pressure, dew point temperatures, et cetera, and really began to kind of crack that egg as it relates to the more advanced things that we can calculate with the psychrometric chart. So why are all of those things important? Why am I reviewing that as it relates to vapor pressure? Well, it starts with temperature. Temperature, if you'll remember from our previous discussions, temperature is a measure of sensible heat. It's the heat or the energy that we can literally feel as a byproduct of the total heat and energy that's present in a material. It's the sensible heat. And what we mean by sensible heat is that materials are comprised of matter, right? We have a bunch of molecules, if you will, that make up a substance. The molecule you see on screen right now would be a good model for a water molecule. But in addition to that, there are other molecules that make up this material, whether it's a 2x4 or a piece of gypsum wallboard, a countertop, it doesn't matter what it is. It's comprised of all of these molecules that make up the material. Temperature relates to the amount of movement that these molecules have. And as they have that movement and the mass associated with that material, we feel the effect of that kinetic energy. So as these molecules kind of move around, that net effect of that movement and the kinetic energy, the weight plus the movement, translates to the actual temperature. And that's sensible. I can feel it on my hand when I touch a material, and the surrounding air, surrounding materials can also feel that, if you will. And that's how energy moves between two different environments, is because of that kinetic force or that kinetic energy. When I increase the temperature or increase the energy, I also increase the movement or the rate of movement or speed of movement. When I increase that rate or that speed, we increase the pressure associated with that substance. So think of it like an analogy. In an analogy here, if I were to take a like 1 gallon paint can and put an inch of water in the bottom of that 1 gallon paint can, seal the lid on that paint can, and then raise the temperature of the room, make the room a little bit warmer, then the liquid in that can would become warmer. More of the molecules would evaporate from the liquid. The gas would all be moving with more force, more energy, and that would exert more pressure on the paint can. Now, if I take the paint can and I put it on a stove and really start increasing the temperature, then the pressure is going to become very immense inside that container, to the extent they'll probably blow the lid right off the top, right? That analogy kind of helps us understand that relationship between an amount of moisture that is in a sealed environment and the temperature, and increasing that temperature so that we get an increase in the pressure associated with the vapor inside that container. And if you think about building materials kind of like that paint can, right? What we understand is that there's a direct relationship between energy and pressure, right? There's a pressure temperature relationship. And that relationship is something that we can measure. It's something we can control. It's something we can leverage in a drying process if we understand how to measure it and we understand how to evaluate it. And not only can we control it, but we can actually use it to predict drying rates. And that's one of the keys that we're going to touch on here in just a moment. It's using it for predicting drying rates. So again, there's a relationship here between the molecules that make up a substance, the molecules of gas that are around that substance, and the temperature or energy in that environment. So let's take a closer look at what that means from a vapor pressure standpoint. So first, let's define vapor pressure. Vapor pressure is the pressure of a vapor in contact with its liquid or solid form. And that's kind of a really fancy way of saying, basically, it's the pressure at that interface between the two. And when I have a liquid, let's make it really simple, a liquid water, and then I have gas of water vapor above that liquid, then vapor pressure is exerting the force of that vapor on that liquid. By association, we can also use that to understand the force of that vapor against everything around it inside that sealed container. All right. And the greater the force, the more likely that vapor is to escape that environment. The other factor that influences that is the permeance, right? How readily can the vapor travel from one side of that can wall to the other side of that wall? And obviously with a aluminum can or a steel can or a tin can, it's very difficult for water vapor to travel through. The permeance is extremely low. Fortunately, building materials are more permeable than a tin can, right? So with all of that said, that's what vapor is by definition, vapor pressure. Let's take a look at it by numbers now. Inside of this sealed environment, the water vapor inside that environment, if I were to use that analogy, the paint can with some liquid water in there, will have a certain pressure. We typically measure that in inches of mercury. At least here in the United States, we measure it in inches of mercury. We would use a metric scale outside of the United States. But what's important is not the scale, it's the number, right? We have a certain pressure associated with the vapor inside that container. When I increase the temperature inside that container, we increase the movement of those molecules. They move more rapidly. They have more kinetic energy, more kinetic force. And if there's any liquid, we evaporate more of that liquid, which adds to the total mass of the vapor. The mass and its energy both together increase the pressure, right? In the outside environment, once I increase the energy inside the container here, we also have a vapor pressure. The vapor pressure associated with the outside environment can also be measured, right? And if the pressure inside the container is greater and the pressure outside the container is lower, then nature is trying to drive moisture out of that environment. If the opposite are true, then nature is trying to drive moisture into that environment, right? Now, it probably goes without saying, and I know it's a bit complicated when you first run through it, but I know it goes without saying that understanding which direction vapor wants to move without having to wait 24 hours to find out whether or not a building material is going to become any drier can be highly advantageous in water mitigation, right? If I know now that water vapor is wanting to move out of the material, that's what nature is driving, then I know we're going to see some drying progress, right? If I know the opposite is true, if I know vapor is trying to drive into the material, right, then it's reasonable to assume that we're not going to see any drying progress. And just imagine some of the projects that you've managed and the projects that you've been on where how valuable it would have been to know ahead of time that when you came tomorrow, there would be no drying progress. If I could know that now, and not only know that it's not going to make any drying progress, but also know that because it wasn't going to make any drying progress, that I would need to make certain adjustments on the job and not have to wait 24 hours to make them, right? To know precisely what adjustment is needed to ensure progress is made in the next 24 hours. In other words, what vapor pressure can allow you to do is to be proactive with your mitigation steps, proactive with your adjustments, know ahead of time, kind of see the future and know ahead of time what's going to happen. It also gives you justification when you can use actual numbers to show here's what's happening with the the placement of equipment, the control of the environment. Here's what was going to happen, aka nothing. Here's the adjustment that I made. Here's how it increased the drying rate, and the reason, therefore, that I made the adjustment. When I can put numbers up against that to show the reason why those changes were made, it can be tremendous justification for the decisions being made on a project. So in this particular example, I want to really drill into these numbers for a second, because we're going to use them quite a bit here in just a moment. Notice that inside of this container, based on the temperature and the moisture content that's present in that environment, there's a gauge on that container that is measuring the pressure, the partial pressure of water vapor in that container at 1.5 inches of mercury. Okay. On the outside, we're measuring it at 0.5 inches. The difference between the two being 1 inch. When we talk about vapor pressure differentials, it's that 1 inch that is the differential. It's the difference between what's in the material or in the container versus what's in the air surrounding that container. The greater that difference, all of the things being equal, the greater that difference, the greater the drying rate. Okay, so keep that really simple part of the math in your mind for a moment, because when we get into the math here in just a moment, it's going to feel a bit complicated at first, but if you can remember what a vapor pressure differential is, it's going to help immensely. All right, so let's take it back to the chart. How do we get the numbers? How do we measure and how do we produce a vapor pressure differential on the chart? And again, this is a bit of review before we get into today's new content, which will be the math. We begin with, on the material side at least, measuring the temperature of the material, all right? Not of the air, but of the material itself. And we've talked about a couple of different ways to measure building material temperature. There's a couple different ways that you can do it. The easiest and fastest way to do it is to ensure that in your inspection kit, you have an infrared thermometer, which looks like a little laser pointer gun, and you shoot that down at the surface of a building material, and it uses the infrared light off of the material to assess or evaluate the temperature of the material. It gives you an instant reading, right? Very, very simple, very low cost device. They're typically less than 90 bucks. In fact, there's a lot of them out on the market today that are 50 bucks or less. So it's a very inexpensive device. In addition to that, a lot of the newer moisture meter kits will actually come with a surface sensing element on board with the meter. Some of them use infrared, some of them use a contact sensor. So there's different ways that you can do it that way. The other way that you can do it is to take that hygrometer, your thermal hygrometer, and measure that humidity associated with the surface of the material under containment. So you put the hygrometer down on the surface, you contain it to the surface, let it acclimate. That reading takes a bit more time because in order to really accurately measure that, you've got to allow that little microscopic layer of air at the surface to acclimate with what's happening immediately beneath that sensor. But the second measurement you're going to need is going to have you doing that anyway, because the second measurement you need is the relative humidity being created by the moisture in the material. This is something we call an equilibrium relative humidity, or ERH. And in essence, what you're measuring is once you contain the air at the surface of a material, what humidity does the moisture in that material create? And on a future episode, we can get a bit deeper into kind of the mathematics behind equilibrium relative humidity. But here's the really, really simple, is that relative humidity is a percentage of saturation, basically. If I'm getting a 50% relative humidity from a material, then in loose translation, what that means is that the material is absorbed, at least the fiber has absorbed at 50% of its total capacity. So there's a direct relationship between the degree of wetting in a material and the relative humidity that material will support, right? So if a material supports a 30% moisture content at fiber saturation, then a 50% relative humidity is half of that. That means the material's at a 15% moisture content. That's the way that math would kind of work in the background. But not really the main point of today's lesson, so I'll kind of bring us back here and off that tangent. We measure the relative humidity being created by the material, the temperature of the material, and we plot these two on a psychrometric chart. These two plotted on a psychrometric chart on the very far right-hand side for most charts is going to give me the vapor pressure associated with that material. And in this case, that vapor pressure is about 0.18 inches of mercury. So what does that mean? That means that there is a force behind the water vapor wanting to leave the material. And that force behind that water vapor trying to exit the material is at 0.18 inches of mercury. And like I would say with any form of measurement, one number doesn't tell me anything. So is 0.18 inches good? Is it bad? It sounds kind of low. Well, it doesn't matter to me until I have another measure to compare it to. And the measurement we need to compare it to is the measurement of the air, right? Now, the air measurement, I'm not going to spend a lot of time talking about because this is a really basic psychrometric measurement. We just grab our thermal hygrometer, we measure the temperature and humidity of the air in close approximation to the material. It's not the air up here at 5 feet. It's going to be closer down to the surface that I'm concerned with. But what is the temperature and humidity of that air? And therefore its vapor pressure. And in this analogy, or this example rather, notice how the air has a vapor pressure of 0.42 inches. At 80 degrees and 40% humidity, we have a vapor pressure of 0.42 inches. Well, that should raise a red flag for you. If the air has a force, the vapor has a force of 0.42 inches, and the material I'm trying to dry only has a vapor pressure of 0.18, what direction is this water vapor traveling? Right? Physics tells me that the water vapor is driving into the material, not out. So is this material going to be any drier in the next 24 hours? Unless there's some much drier condition on the opposite side, no, right? This material is likely going to become wetter in the next 24 hours, not drier in the next 24 hours. And what's interesting from this is that you wouldn't think with that initial look that a 40% relative humidity environment, my air is at 40% relative humidity. That doesn't sound like really wet air. So why is that making a building material wetter? And the reality is because the material is pretty cold, the air is relatively warm. But if you really want to distill it down to the simple truth, the air has a higher vapor pressure, and pressure drives movement, right? The movement of that water vapor is going to be dictated by the pressure differentials. And the pressure differential shows me which way this water is going to move. I don't have to wait 24 hours to know that this material is not going to make progress. I'm going to know that right now. Now, that's the easy part. You know, stating the problem is the easy thing. Stating the solution is the more difficult part. So how do I solve this and how do I fix this? Well, what we need to understand is something I said just a moment ago. If the material is giving off a 50% relative humidity, if that's what it's supporting under containment with a hygrometer right at the surface, the equilibrium relative humidity is at 50%. The reason it is because of how much moisture is in the material. And that material will support a 50% relative humidity no matter what its temperature is, because that's dictated by the amount of moisture that's in it. So if we increase the relative humidity, right, or increase rather the temperature of the material, the relative humidity is not going to change. It's going to remain the same. So let's kind of break that down here a little bit on the psychrometric, or on our analogy. If my vapor pressure in the air is higher, the vapor pressure in the material is lower, we're driving the wrong direction. In order to fix that, we can raise the temperature of the material. So notice here on my chart, I've gone from 50 degrees with my material, and I've raised that all the way up to 90 degrees. Different ways to do that. If it's a subfloor over a crawl space, we could heat the crawl space. We could use radiant heat. I could just raise the temperature of the entire built environment. There's different ways that we could do that. Let's not worry about the method for a moment. Let's just worry about the physics. So if I take 50 degrees and raise that to 90 at the same relative humidity of 50%, notice the new vapor pressure of my material. The vapor pressure of the material is now 0.71 inches. In essence, what we've just done is taken the paint can with a little bit of water in it that was 50 degrees, sealed the lid, and then moved that paint can over to an environment where the paint can became 90 degrees, right? By raising the temperature, the pressure associated with the vapor internally is going to increase. There is now a greater force inside the can. Not only is it greater, the force inside the can is now greater than the force in the air outside the can. Now vapor wants to move in the correct direction, right? Now it wants to move the proper way. So that was what we had covered up to this point, right? It's just understanding how to look at that vapor pressure differential, how to measure that vapor pressure differential. What we didn't get into is what that really means. What does that translate to? So we're going to get a little bit deeper now in the technical and start driving this conversation a little bit further. To go there, here's what I want to draw out first. The vapor pressure differential in this example is 0.29 inches. The container, the material, has a vapor pressure of 0.71. That's a 90-degree material at 50% relative humidity. The air has a vapor pressure of 0.42. The difference between those two is 0.29. That's the vapor pressure differential, right? That's what's driving the drying process for us. So let's learn what that means. So how much does vapor pressure really matter? To understand that, we have to define the term permeance for a second. Permeance is the ability for vapor, you can insert whatever you want there, but in this case, we're talking about water vapor. It's the ability for vapor to flow through another substance, right? So if I have humidity, moisture in the air, and we put, a plastic sheet down the middle of the room, and I have a different amount of moisture on the other side of the room. Permeance is the ability for that plastic sheet to allow the water vapor from the higher humidity to the lower humidity to flow through it. At what rate does it flow through it? And permeance is expressed in a very specific scale. Permeance is expressed in grains, which should sound familiar to you, right? We measure humidity in the air in grains per pound. Grains of water vapor per pound of air. And the quick trivia question is, how many grains are there to a pound of water? There are 7,000, right? So a grain is 1/7,000th of a pound of water. It's not a lot of water, right? But that's what we measure permeance in. We measure that per square foot of material. So a sample of the material that measures 1 foot by 1 foot per hour. So how much of it moves in a 1 hour period, when the vapor pressure differential on either side of that substance is at 1 inch. That's what permeance is. So when you see something has a perm of 5, right, then what that means is that 5 grains of water will travel through 1 square foot of the material per hour if there's a difference of 1 inch of mercury, right? That's the vapor pressure differential is 1 inch. So that kind of grounds the meaning of permeance for you just a little bit so we understand what perms are. So let's take that and translate that into a little bit of math. All right. So what I want to know is I want to know how much water is going to come out of this building material. So that's going to be G. That's the grains of water. So we're going to use a value here for the square feet of material. We'll call that M. We're going to use a number of hours. We'll call that H. And then we're going to have a vapor pressure difference, right? A vapor pressure differential. We'll call that VP. And then we're going to have a perm rating, right? What's the perm rating for the material? How many grains travel per hour, et cetera? We'll call that P, all right? When we assemble all of this into some math, this is what it looks like, all right? Now, you may all of a sudden go cross-eyed, especially if math is not your favorite subject, but don't worry, I'm going to do all the math for you. Having said that, this is a method, all right, that if you deal with difficult building materials, if you deal with high value assemblies, if you deal with clients where the drying rate is far more important than any other property associated with the project, this is something that you're going to want to understand. And it's something you'll want to be able to crank out when you need to crank it out. Personally, what I do is I put it all in an Excel spreadsheet, makes the math really, really simple for me, so that I can calculate drying rates pretty quickly just by putting in a few psychrometric values. All right, so here's the formula. Here's the calculation. Let's run through the math. So how much water is going to come out of the building material? I'm going to calculate that by saying if I have 1 square foot of the material times 24 hours, because I always think about a job per day, right? So we use 24 for hours. And then I've got to plug in what's the vapor pressure difference and what's my perm rating. Those are the two things that I'm missing. So that's in square feet of material. That's in hours per day. What is my vapor pressure differential? What is my perm rating? So I'm going to use, as a perm rating, I'm going to use a plywood composed predominantly of Douglas fir. Just standard plywood made of Doug fir. Its permeance is going to be 1.9. So that's the perm rating of a standard sheet of plywood. The example vapor pressure difference I'm going to draw from our last slide. The vapor pressure difference we calculated in that slide was 0.29 inches. So what is my drying rate going to be from this piece of plywood given those drying conditions? Run the math. We plug in 0.29 for my vapor pressure difference and 1.9 for my perm rating. And here's what we come up with: 13.2 grains per day per square foot. So think about that for a second. 13 grains. How much is a grain of water? A grain of water is 1/7,000th of a pound. So I'm going to get 13.2 7/1000ths of a pound per square foot per day. That's not a lot of water, right? It's not a phenomenal amount of water. So sure, we're going to have drying and we're going to have progress. And if I wanted to run out that math even further, if I get 13 grains, that's 13/7,000ths of a pound, I could figure out, for the entire surface of the material, if I knew it's square feet, how many pounds of water that is, and is that really going to get me to a reasonable approach to my drying rate? Real simple math, though. 13.2 is not much. So what can I do about it? How can I fix it? How can I change it? First and foremost, I don't necessarily have to. It is drying. I am moving in the right direction. But if I want to speed my rate and I want to put some resources behind doing so, let's find out what benefit we'll get from doing so. So let's come back to our psychrometric chart here for a minute. We got 0.29 inches, the difference, because of the materials conditions and the air's conditions. So here's what we started with. The material is 90 degrees at 50% relative humidity. That's giving me a 0.71 inch on the material side. That's where I got that vapor pressure from. On the air, I've got 80 degrees at 40% relative. That's giving me 0.42 inches. Let's play with the air first and manipulate the air. The best way to change the vapor pressure associated with the air is to simply lower its humidity, right? If I lower the humidity of the air, the moisture content of the air, I will reduce the weight of that water vapor, the pressure associated with that water vapor. So let's take a look at making a minor change here. Let's take the relative humidity from 40% and let's drop it down to 30%. Notice what happens to my vapor pressure. So I'm going to roll back one slide and look at the vapor pressure again. I'm going to go from 0.42 down to 0.32. So I lost 1/10 of an inch by dropping it down 30% relative humidity. That's going to help, right? My differential is now 0.39. It was 0.29. It's now 0.39. On the other end of it, if I want to manipulate the vapor pressure differential in the material, again, it's the temperature of the material I've got to change. The relative humidity supported by the amount of moisture in the material is going to remain the same. That's not going to change until the moisture content does. It won't drop until the moisture content drops. So it's the material temperature we're going to manipulate. So let's take the material temperature and let's raise that temperature another 10 degrees. And notice what happens to the vapor pressure. Again, I'm going to roll back and forth between these two slides a couple of times. Notice that we were at 0.71 inches with the material. By raising 10 degrees, we're now at 1 inch, right? That's a good jump. It's a pretty healthy jump, going from 0.71 all the way up to 1 inch. So notice how much impact there is from a 10-degree rise in a building material versus a 10% drop in relative humidity. There's a huge impact by raising the temperature of the material. That doesn't mean we want to make all of our building materials 200 degrees Fahrenheit, right? There are some limits, and we'll touch on that here in a moment. But just notice the difference in impact. The energy that is applied to the building material has a huge impact on that vapor pressure differential. Now, by making both of these changes, we've jumped our vapor pressure differential all the way up to 0.68. We were all the way down at 0.29. So how does that translate to my drying rate? We were at 0.29 inches. by making a 10% drop in RH for the air and a 10-degree increase in the building material temperature to, moderate adjustments, not huge. Now we're at 31 grains per square foot. We've more than doubled the drying rate. And if I more than double the drying rate, then what's going to happen to the drying time? More than double means I'm going to cut it down by more than half, right? So if it was going to take me 5 days, for example, it's going to take me somewhere less than 2.5 days. It makes a pretty substantial impact on the drying rate. Now, a couple things here that I want to reiterate that we opened up with. Do I need to run this math on every building material and every project? No. Right? You can tell just by running through the math here that there's definitely some complexity associated with really truly evaluating vapor pressure differentials. Having said that, if I'm dealing with a property where the most important attribute of that project is the drying time, this is going to add a lot of value. Where I'm dealing with really highly sensitive building materials that have extremely high value, and right next to that, I've got building materials that are really wet that don't have a lot of value, but the moisture that they're letting off in the environment could impact a lot of other things, then vapor pressure differentials can have a substantial amount of value. So I can give you lots of scenarios like that where understanding vapor pressure differential is going to bring a tremendous amount of value into the project, especially in those types of special cases. So in those circumstances, that's when you really want to run through and do the math, because that's when it's going to bring in a lot of value. So let's round this back into the H.A.T example again. So we started off with this as a quick review on H.A.T. I want to, as we come closer to the end of this, I want to come back to that concept. So again, this model, I really like this model because it helps us understand when vapor pressure becomes really critically important. At the front stage of a project, the most important attribute of my drying resources is good airflow, good air movement, because we're dealing with surface water. We're dealing with what I call the easy water, right? And as long as I've got really good rapid transportation, I can remove that saturated humidity from the surface, get it up into the air, let my dehumidifiers process it or ventilate it, whatever we're going to do with it, and replace that humid air with something drier than 100%, right? And that's going to sustain a drying rate initially for me. So air movement is absolutely critical. There's a calculation out there that we'll talk about in a future episode that's referred to as Dalton's law of evaporation. And the really simple in that calculation is that air flow, when you're talking about a surface of liquid water, that air movement is a multiplier on the drying rate. And in general terms, the faster the air movement is, the faster the drying rate. As soon as that surface water is gone, however, and we no longer have moisture right at the surface, the air movement's impact begins to diminish because air movement is no longer in direct contact with saturation. At that point, lower humidities become more important, warmer temperatures become more important, warmer temperatures of materials. As we move into bound water, that becomes even more extreme, right? That's when vapor pressure really becomes critical. So why am I bringing us back to this model again? Here's another way to understand when evaluating vapor pressure becomes valuable. I don't necessarily have a lot of value in hard analyzation of vapor pressure on the first day, right? Because air movement's my primary drying force on the first day. I need enough humidity control to keep up, to prevent the humidity from skyrocketing and causing secondary damage in other areas. But what I really need most is lots of airflow. Once the surface water is dissipated and we begin working on free water, air movement's still going to do a lot of the bulk for me because there's still saturation in there. It's just not at the surface, right? As we start to transition out of free water and move towards bound water, and you've been monitoring for 1 or 2 days in the drying process, monitoring moisture contents, et cetera, that's the stage in the project where you're really going to be seeing the areas that are going to be a problem, right? The areas that are not making the same drying rate, they're not making the same drying progress. And that's when you can identify those 3 or 4 areas that look like they're going to take 5 to 7 days to dry, if not longer. Well, everything else is going to take 3 to 5 days. It's those areas where I'm going to start breaking out the vapor pressure tool and start understanding what's happening with those materials specifically using vapor pressure. Because if I can analyze those with some vapor pressure differential, just those problem areas, and cut those drying areas in half by understanding what my targets are for air, humidity, and material temperature, then all of a sudden I can bring those down to closer to a 5-day dry time and not a 7 to 10 day dry time because of them being problem areas. I don't have to react to an adjustment. right? Make an adjustment, wait 24 hours. Did it work? No. Well, shoot, we'll make another adjustment. Did it work? No. Instead of that, I can say, what are my vapor pressures associated with the air and the material? If I make this adjustment, how much impact will it have? Will it reduce my drying rate by half or very little? Is it therefore worth my effort? It gives me the ability, like I said, to be proactive instead of reactive when we're dealing with those problem areas. Okay. All right. So again, we see that humidity and temperature become much more important through the drying process in the later stages. That really directly translates to vapor pressure differential, whereas air movement starts out strong, most important resource rather, and becomes much less impactful as we move later into the job. All right. All right. So with all of that said, a couple things here I want to kind of review in simple terms to really drive home the importance of the concept that we talked about today. So vapor pressure in review. First of all, vapor pressure is the driving force behind your drying rate. Permeance is the resistance, but vapor pressure is the driving force, right? It's the driving force. To kind of take that one step deeper, humidity is the primary part of the vapor pressure associated with air. And by humidity, I mean your grains per pound. The higher your grains, the higher your air's vapor pressure. The lower the grains, the lower the air's vapor pressure. So one really direct way to change vapor pressure differential, obviously, is just make the air drier, right? The lower the humidity in the space, the lower the air's vapor pressure. On the other side of that coin, the vapor pressure associated with the material is a direct component of the material's moisture content and its temperature, right? And again, I'm going to use that analogy because I know a question popped up about the relative humidity and the moisture in a material and that relationship. Wood has a saturation point of 30% moisture content. The fiber saturation point for most species of wood is approximately 30% moisture content. It can be wetter, but the other water that's in that wood is liquid. It's not absorbed. It's in all the pores and capillaries and air pockets inside the wood. Once wood gets up to 30% moisture content, technically it has absorbed all of the water that it can. Okay. Everything else is kind of adsorbed, all right, which is a whole different type of sorption. So 30% moisture content is the saturation point for wood. So if I'm getting a 50% relative humidity in equilibrium at the surface, then that wood is at approximately half of its saturation, or 15% moisture content. All right. And that can be kind of a mind bender for some of us, because we always think of these percentages being 0 to 100. But when we're talking about percentage moisture content, it's not at 0 to 100. Percent moisture content is the amount of water in a material expressed as a percent of the material's dry weight, right? So if I say that wood is at 30% moisture content, what I'm saying is that it's holding on to 30% of its dry weight. It's a percent of its weight, not a percent of 100, right? It's not an exam score, right? Whereas humidity is kind of like an exam score, right? It's 0 to 100. 0 is the least you can have in relative humidity, 100 is the most, okay? So theoretically speaking. So anyway, back on point. So moisture content and temperature are what dictate the vapor pressure associated with the material. You have to change one of those two to change the material's vapor pressure, okay? Moving on. Airflow is also therefore important because I have to ensure that the humidity in my air, the vapor pressure in my air, right, is in direct contact with the evaporating surface. And we spent a lot of time really beating up on how important this is. There always needs to be at least some air movement present to ensure that the dry air that we're producing, however we're producing it, is in direct contact with the material. The reason why air movement's importance begins to tail off towards the end is because the evaporation rates are so slow. I don't need a lot of air movement to keep that dry air in contact with the surface. There's not a lot of water leaving the material, right? And the less water there is leaving, the less transportation I need to carry it away, okay? All right, so that's the quick review. We're going to jump into the Q&A session here in just a moment. Before we do, let me close out the live side of our presentation with just a couple of quick notes. Again, this was Technically Speaking, episode number 5, a very technical episode digging into vapor pressure. Again, my name is Brandon Burton, your host today, and I will be your host throughout, technically speaking. This was episode number 5. We're going to have on our next episode, number 6, maximizing humidity control as a resource. So mark your calendars for that. It's going to be June 21st. We're going to dig really deeply into managing dehumidification, using open air exchange, using heat and air exchange as a way for humidity control. So we're going to get really deep into understanding how to manage humidity within a space and all of the different ways that we can leverage resources on any given project. So that'll be coming up June 21st. And with that, we're going to roll things over into the Q&A period.